All right, so Unit 4 is on our exponential functions. We're going to take a look at some of its characteristics and properties first. Your parent function y equals a b to the x is that parent function for an exponential. I want to show you really quick what you would see on your EOC on the formula sheet in terms of your exponential functions. So if we pull that up really quick, here you can see you've got that same function given to you for that parent function. Okay. Also under exponential functions, you have your recursive formula and your explicit formula, and you also have compound interest. This is your growth formula, but this is specific for money problems. But it's the same concept for most of your growth problems. You just don't have the n involved when we're talking about growth and decay. All right, so back to this, just to kind of talk about how we would graph an exponential. Remember, we use k right here instead of c. They use c. But k, that's that asymptote. So if you have a number that's added or subtracted from the end, that's going to tell you where your asymptote is, that brick wall that your function cannot cross. A is your initial rate or your initial value, excuse me, and b is the rate at which your function is either growing or decaying. So in this function here, we have f of x equals 2 to the x. My asymptote is at 0. See how my function is approaching the line y equals 0. I also know that because there's nothing at the end of this function. It would really be like I had a plus 0, so that's my asymptote. My y-intercept is at 0, 1, and I have an example here of growth. Some little keys to remember about our characteristics. We know that we're going to graph above or below the asymptote. If you have a negative out front, you're going to have something that would be below the asymptote like this. Whereas we had a positive, so it's above the asymptote. If you have a number that is greater than 1 as your base value, that rate, that's going to be growth. If your number is between 0 and 1, it's a fraction between 0 and 1, that's going to be an example of decay. Okay, that's when we're falling. Like that, or you could have something like that. Those would both be examples of decay. And then your C value, or as we like to call the K, that's that number at the end. So right here, my asymptote would be at 3. If you're just given something that's in more of a parent function notation, there's nothing at the end, it's really plus 0. Okay, that's your asymptote. And to find your y-intercept, remember you let x equal 0, and then you can solve to figure out what your y-intercept is. Whenever you have a parent function with nothing at the end, your y-intercept for an exponential is going to be at 0, 1. So graphing those, you can use those properties. Like here, I know that this is greater than 1, so I should have something that's growing. I should have a growth problem, and I have my 2 right here. This indicates my initial value. Remember, when you're graphing, you can always use a table. If you forget all of the features of the specific graphs, just use a table. So plug in your values from -2 to 2 in for your x and get your y values out, and then you can plot your points. So that's what we did here. The other things that you can identify your domain and your range. So we can plug in any value for x for an exponential function. That's the same for linear functions and quadratic functions and exponential functions. The domain is going to be all real numbers, unless you're in a word problem. Sometimes there's more specifics, but if it's just a general graph, domain is all real numbers. And then our range here, notice my y values, they're going to start at 0. So we could say that y is greater than 0. They've also listed it here in set notation. Notice that they use a parenthesis here to show that it doesn't include 0. If it included 0, like if I had greater than or equal to, I would use a hard bracket to indicate that it includes 0. So that's just a little difference in the notation there. They did the same thing over here. They made a table so that they could plot those points, but they also identified some of the characteristics. So we know it's above because I have a positive. I'm going to be decaying because my base value, that rate, is a fraction between 0 and 1. So notice my graph is decaying. My asymptote is going to be at y equals 0. Okay, so my asymptote would be right in here. And my y-intercept, when I plug in 0 for x, I get 4 out. So there's my y-intercept. Then they just plugged in our points, -2, -1, 0, 1, and 2, in for x to get out our y values and plotted those. Transformations. We talked about transformations with our quadratic functions. It's the same sort of set of rules. So when we add or subtract a number at the end, that tells us if we're moving up or down. Okay, these are the ones I want you to remember. So +5 means we move up 5. When you have something inside the parentheses like this tells us if we move left or right. And it's opposite. Remember, we talked about Hank and Kelly if you're in my section, and Hank lies. This is H, okay? So since it says -5, we're really moving in the positive right 5 units. Number out front means that I have a stretch with a factor of 4, and that negative out front means we reflect over the x-axis. If you want to look quick, I'm going to pull up my graphic for you guys so you can see that. Okay, here are those function rules right here. You might just want to take a look at these the morning before your test, just to kind of have them in your mind. You could even, once you get your scratch paper and you're allowed to write, just kind of jot those down if it's something that you're kind of, trying to remember and think to yourself. There probably won't be a ton of transformation problems, but there might be a couple on the EOC. Okay, so back to our slides. Okay, then our characteristics, remember we have that domain and range. We know domain's all real numbers. The range and the asymptote are going to go hand in hand. If my asymptote here is at 2, then my range has to be everything greater than 2. Your function for an exponential is never going to cross the asymptote. My y-intercept here we can see is at 0, 7. Remember, this is when x equals 0. And my end behavior describes what's happening to the graph. So as my x's are getting bigger and bigger, my line is approaching y equals 2. Okay, so that's this one right here, this bottom one. And as my x's are getting smaller and smaller, they're getting more and more negative. Notice I'm approaching positive infinity, and that's what we have right here. We are never increasing in this function. This is a decay problem, so we are always decreasing from negative infinity to positive infinity. Okay, average rate of change. We talk about average rate of change with all of our functions, linear functions, quadratic functions, and exponential functions. It's the same thing every time. You are basically taking the idea or the formula for slope, y2 over y1, y2 minus y1, over x2 minus x1. Okay, so that's what we're doing. So here it says find the average rate of change on the interval of x equals 0 to x equals 2. Those are my x values. You have to find your y values by plugging in your x's to get your y's, which we did right here. So here are my 2 points. So this would be like my x1 and my x2. Oh, I lied. My x1 and my y1, excuse me, and then my x2 and my y2. And then we just used our slope formula. So -11 minus -5, that gave me a plus, and then 2 minus 0. It's -6 over 2 is -3. That is my average rate of change. They did the same thing here with the table. They said to find the interval between f of -4 and f of -2. These are the x values I'm looking at. So here's my x1 and my y1 and my x2 and my y2. And you're just using this formula. So really quick, let me show you on your formula sheet. Notice at the top you have your slope formula right here, and then right next to it it says average rate of change is the change in the y value. Here's the change in the y value divided by, there's that fraction bar, divided by the change in the x value. So you're going to use this slope formula whenever you're thinking about rate of change. All right, arithmetic and geometric sequences. Arithmetic sequences are actually linear. Okay, so this would be a linear function. These geometric, are exponential. Okay, so right here I said arithmetic sequences, they have a common difference. Okay, that's that d value. That's when we take our second term and we subtract it from our first term to find our d. And then geometric sequences, they have a common ratio. Okay, the common ratio, you're going to take your a2 and divide it by your a1 to get your r value. Again, the a and the d are not on your formula sheet specifically, but your explicit and recursive rules are. So let me just pull that up really quick. So notice under linear formulas, you have your arithmetic sequence. There's that D for that common difference. And then here is your geometric formula. Okay, and there's the R for the common ratio. All right, so the other thing, really what you need for either formula, you need to know your first term and you need to know your common ratio when we're talking about exponential functions. So right here, the first thing I want to do is identify whether or not it is linear or exponential. So I look to see if there's a common difference. So if I take a2 minus a1, I get 10. 12 minus 2 is 10. If I take 17 minus 12, I only get 5, so it cannot be arithmetic. It's not a linear difference. And then if I look to see if it's exponential, I look for a common ratio. So 12 divided by 2 is 6, but 17 divided by 12 is not 6. So this one is neither. It's neither arithmetic or geometric. Whereas in example 2, if I look here, if I take 40 divided by 80, I get a half. 20 divided by 40, I get 1/2. 10 divided by 20, I get 1/2. There's a common ratio. That R value is 1/2. My first term is 80. A1 is 80. So then notice here we wrote the explicit formula right here, okay, using this formula. So a sub n equals 80, that's my first term, times 1/2 is my ratio to the n minus 1. You're just plugging in the values of a sub 1, your first term, and your common ratio. And then number 3 happened to be arithmetic, because as I go, 13 minus 4 gives me 9, 22 minus 13 gives me 9, 31 minus 22 gives me 9, 40 minus 31 gives me 9. I'm adding 9 every time, so this is going to be an arithmetic sequence. My first term is 4, my common difference is 9, so now I can use my formula for my arithmetic explicit formula. So a sub 1 was 4. My common difference was 9, and we have to do a little simplifying here because I have this set of parentheses, so I've got to shoot that rainbow through. 9 times n is 9n, 9 times -1 is -9. We simplify, 4 and -9 are like terms, 4 minus 9 is -5. This is my explicit rule for that arithmetic sequence. All right, some applications of exponentials. We are not covering this. Some big things here. Sorry, I'm just looking. Things we didn't talk about. Okay, so the number of bacteria in a petri dish doubles each hour. So here's my rate. Okay, it tells me how fast we're increasing. So it doubles each hour. There were initially 300 bacteria in the dish, and then when the scientists checked again, there were 4,800 bacteria, and we want to know how much time has passed. Okay, so since my initial value is 2, my my rate was 2, my initial value was 300. Remember that my formula for my exponential is a times b to the x, okay? A is that initial value. My b is that 2. That's the rate, 2 to the x. And I know that it's going to be eventually 4,800. That's where we're getting this step right here. Okay, so what I would do instead of solving this, because we didn't talk about how to solve for exponents like this, is take your answer choices and plug them in. You know how to write the equation, so take your choices A, B, C, D, plug them in, and see which one works, which one gives you 4,800. Kind of work backwards on that one. Okay, so here, this is really what we focused on. This is, I'm sure you'll have a growth or decay problem on your EOC, and your growth and decay looks something like this. Okay, so it's just an exponential function. If it's growth, remember, we have 1 plus the decimal, and if it's decay, we have 1 minus the decimal. We're just filling in the growth rate. This is our initial value. This is our variable, and you can let it be x, you don't have to let it be t. And then this is that growth or decay decimal that we're going to put in. So here it says that the PTO membership has increased, so we're going to be adding each year for the past 5 years. Okay, there's my time. By an average of 6%. Okay, so there's a rate. So if there are currently 211 members, there's my initial value, okay, my B. How many members will there be after 10 years? Okay, so here we have our initial value. This is my growth rate, 1 plus my decimal of 0.06, because remember 6% as a decimal, if we divide that by 100, gives me 0.06. And then I want to know after 10 years, so I'm raising that to the 10th power. And that's what we get, 211 times 1.06 to the 10th gives me 377.86. We can do the same, apply the same idea to money. So we bought a car for $18,500. That's my initial value. Okay, the car is going to depreciate or get less by 5% every year. Okay, so over here, here's my little info about that. So 5% equals 0.05. So 1 minus 0.05, because this is decay, we do 1 minus the decimal, we get 0.95. So here's my function. 18,500 times 0.95 raised to the x, and I want to make a prediction after 5 years, so I plug in 5 for x. All right, so that wraps up our section on exponential functions.